아니지.
Hello everyone, welcome back. We've passed the midterm, so hopefully that gives you some relief. We're going to continue and finish chapter 14 today. The only announcement is just don't forget you have an achieve due Monday. It's a shorter one just to finish up 14. And then we got to the beginning of 15 and 9 a.m. in my 9 a.m. section, so we'll try to get there as well. But first, let's remember what we were discussing on Monday, which was these elementary steps. So remember, a overall reaction mechanism often contains multiple steps. We call those elementary steps. So we had this example here of photosynthesis that requires many steps. Here's a picture of the Calvin cycle. In each place where you see a new molecule is one elementary step, one reaction. So step here, something else is produced, ATP is converted, that's a chemical reaction, and then more and more as you go around the circle. So we call these elementary steps. Elementary steps each have their own activation energy and their own transition state. And so as we go through a complete reaction with multiple elementary steps, we pass through different transition state energies. And if we're not at the very last step to produce the final product, then we are producing intermediates. And then the intermediate will continue and react through its own activation energy and transition state. So we looked at this example where this overall reaction, nitrogen dioxide, carbon monoxide, produces nitrogen monoxide, carbon dioxide. And this occurs through two elementary steps. The first one produces one of the products, NO, and it produces an intermediate. We call this an intermediate because it's used up in the next reaction, and then we produce the final product. And so we can use elementary steps of an overall reaction to determine its rate. And we can go directly from an elementary step to the rate law by determining the molecularity, how many reactant molecules are present at the beginning of the reaction. So we started with this one. If our elementary step has one reactant molecule, AB here, then we call it unimolecular, unique for one, like a unibrow. And then the rate is equal to the rate constant times the concentration of that single reactant. Raised to the first power because its coefficient is 1. If we have two reactant molecules like A and C for this second reaction here, two reactant molecules, we call that a bimolecular reaction. Because for that elementary step, two molecules are required. And so the rate is equal to rate constant times the concentration of each of those reactants. Bimolecular reactions have their reaction order is 2. They have a reaction order of 2. Overall. It's first order with respect to A, first order with respect to C, so second order overall. Two reactants, bimolecular, reaction order of 2. If we have two identical reactant molecules, so for this elementary step, we need two A molecules to form the product. We still need two molecules for that reaction to occur, so it's also a bimolecular reaction. We use the same word here. And then the rate is we still have a second order reaction, but now we just have one reagent, so it's raised to the second power for this one. And then lastly, this last elementary step here, we have 3 reactant molecules. We have 2 A molecules and 1 B. All 3 are required for this elementary step to occur. We call this a termolecular. The molecularity is T-E-R, molecular. This is pretty rare for an elementary step. Still possible. And then the rate, we follow the pattern. So we have A squared times B, concentration of B. Now we can only go directly from elementary step to rate law if we know it is an elementary step and not an overall reaction. But we can use elementary steps to describe the rate law for an overall reaction, and we'll do that later in a couple of slides. So let's do this example here, this learning check. We have two elementary steps here that describe the overall decomposition of N2O, dinitrogen oxide. This molecule decomposes into nitrogen and oxygen through this two-step mechanism. So for each elementary step, first identify the molecularity, then write the rate law for that step, and then write the overall equation. So you write the overall equation over here. And then we'll do step 1 and step 2, molecularity and rate law. So this question, I think, is just molecularity. There's two questions here, and I think you're just identifying molecularity of step 1 and step 2. So once you complete that, work on the rate law and work on the overall reaction. So 1 more minute. Okay, ending it here. All right, first step, we have one reactant, N2O, and that's it. And there's only one. It has a coefficient of 1, so its molecularity is unimolecular. And the rate law is rate constant times the concentration of that reagent. For step 2, we have two reagents, N2O and O. Two reagents for this elementary step means it is a bimolecular step, 2 molecules required. And so its rate is K times the concentration of each one, N2O times the concentration of O. So it is a second order reaction overall, bimolecular because 2 molecules are required for that elementary step. For the overall reaction, now we need to look at reagents, products, cancel anything out if it is present on both sides. So first, we'll do all of the products. We look at the first product in step 1, that's N2O. And then we look to see if N2O is present anywhere else. It's present as another reactant in step 2, and that's it. So that means for the reaction overall to occur, we need 2 moles or 2 molecules of N2O. The only other reagent is oxygen. Oxygen, O, is also present on the product side in the same mole amount, so 1 mole of reactant for every 1 mole of product. And so they cancel out. Do you remember what word we use for what O is here? It's an intermediate. How do we know it's an intermediate? So it is in both steps. It gets canceled out because it's a product on one side and reactant on the other. But it's important that an intermediate is first produced and then it's used up. We're going to talk about the opposite later today, and that has a different term. So something that is produced in one reaction and then used up in a later reaction, that is an intermediate. And that's all of the reagents. So now we can go to products. First is N2, and there are 2 moles of N2 on the product side. And then we have O2, and there's only 1 on the product side, nothing on the reactant side. So this is the overall reaction equation that occurs through those 2 steps. So if each elementary step has its own activation energy, has its own rate law, then how do we write the rate law for the whole reaction, the overall reaction, the sum of the 2 elementary steps in this case? Well, usually, if we have 2 or more elementary steps, they'll occur at different speeds. They have different rates, they have different rate laws. The overall reaction can only be as fast as the slowest elementary step, because the slowest elementary step will set the pace for the overall reaction. If that's the first step, and then that produces an intermediate for step 2 is quicker. Well, for step 2 to occur, we're waiting for step 1 to complete. Or if step 1 is fast, step 2 is slow, then the product can only be formed at however fast step 2 is going to occur. So for the rate of an overall reaction, it is no faster than the slowest elementary step. And we call this step for a reaction mechanism that has multiple steps. This is called the rate determining step because it determines the rate of the overall reaction. So that means now that the rate of the overall reaction is only dependent on the rate of the rate determining step. So as long as you know the rate law of the rate determining step, you know the rate law of the overall reaction. They'll be equivalent. So rate law for the overall reaction is equal to the rate law for the rate determining step. So in this diagram here, we have a reaction coordinate diagram. We can see it's a two-step mechanism. There are two transition states, two activation energies. One of the steps is faster than the other. One's slower, one's faster. So thinking about activation energy, what that means, transition state energies, keeping in mind that this y-axis is potential energy, so relative energies of these different states of the reactant molecules forming the products. Think to yourself, and when you're ready to discuss with someone around you, which step 1 or step 2, do you think is faster for these? Think about what has to occur for that step to happen, going from the beginning to the end. All right, what are you thinking? I hear it quieting down in here. What are some of the things that you considered, or one thing that you considered? Were you going to say something? Step 2. You said step 2 is faster. Is that what you're, okay. What were you going to say?
I said step 2 because it needs less energy, so we have to get there faster.
Okay, so step 2, I hear 2 votes for step 2, and we're thinking about energy. So it requires less energy, so it'll happen faster. Okay, other thoughts? Anything to add to that? Looking for at least one more comment.
Yeah, I was going to say because the reaction progress is like smaller.
Okay. Okay. So you think about x-axis distance. Okay. Okay. Thank you. All right. So when we are looking at a reaction coordinate diagram and trying to determine faster or slower step, we do need to think about activation energy. So the activation energy for this first step So activation energy for step 1 is about that relative amount of energy. For step 2, we're starting at the energy of the intermediate and going to the transition state. This is a much smaller activation energy for step 2. So imagine reactant molecules are at a certain energy, but that's an average energy. Some of those molecules will have sufficient energy to overcome this activation barrier, or have enough energy to match the activation energy, and then can form the product, or the intermediate. The intermediate is existing at a higher energy, so it already has a lot of energy, and it just needs a little bit more to get to the transition state and then form the product. So because there's so much more energy required for step 1 relative to where we're starting, this is the faster reaction, the slower reaction, this one's lower. The second one is the faster reaction because of that lower activation energy. So higher energy transition state, more activation energy required, that is a slower step. This is our rate determining step here. So highest activation energy means we have the slowest step. Which is the rate determining step. So you can tell, based on this diagram, that the first step is the rate determining step. So if you were given a diagram and you have two different transition state energies, two different activation energies, you can identify the slower step, you can identify rate determining step. So that's one way. The other way is on the next slide, is to be told which step is slow and which step is fast relative to each other. So this reaction is the reaction of nitrogen dioxide, carbon monoxide. The first elementary step is slower than the second. So that tells us that this first step is the rate determining step. We could use the reaction coordinate diagram on the previous slide to describe this overall reaction. The first step is slower, has higher activation energy. The second step is faster. For this reaction, write the rate law. For the overall reaction equation. See what you're taking for the rate law. Okay, what do we know? Don't tell me the answer yet, but what do we know about the rate of this reaction? What does it depend on? So we're thinking about the rate of the overall reaction. What does the rate of the overall reaction depend on? Step one. Why step one? It's the rate determining step, and we know that because it's labeled as slope. So the rate of the overall equation depends on the rate of step one. Step one is an elementary step. So we can take that reaction equation and directly write the rate law for step one. That's the rate law for the overall reaction. Step 2 is fast, so that doesn't have an impact on the overall reaction rate. So with that in mind, what's the rate law? K times what? A squared, is that what you said?
Yeah.
It is something squared, but not A, because we have more details here. Yeah. NO2 squared, yes, because step 1, we have 2 NO2 molecules required for the step to occur. So it's dependent, the rate is dependent on the concentration of NO2. And since there are 2 required, we have NO2 squared. Bimolecular reaction. So this is the rate law of the rate determining step, RDS. And that is the rate law of the overall reaction. Okay, questions on rate laws? What questions do you have?
Why is it based on step 1 and not the overall?
Based on step 1, because the rate of the overall reaction is reliant on the slowest step. So the second step is fast. That will just keep occurring as soon as it has the intermediate. As soon as the intermediate is produced, it will occur quickly. So the slower step determines the rate of the overall reaction. Yeah. Questions? Okay. Okay, we will move on then to the next section, catalysis. So we will learn about catalysts. Now remember, I'm just pulling up this to show a reaction coordinate diagram. Molecules for any reaction require that they have a certain amount of energy, we call that the activation energy, for a reaction to occur. It has to overcome the activation barrier. We can add energy to reactants by increasing the temperature, and that increases the number of molecules that have sufficient energy to overcome that barrier. But it's not changing the amount of energy required, it's changing the amount of energy held by the reactants, which can speed up the reaction. A catalyst also speeds up the reaction, but through a different way. For this reaction coordinate diagram here, we have reactants, products. Typical reaction requires this much activation energy to reach the products. Again, you could increase temperature, that increases the energy of the reactants, but the activation energy is still the same. A catalyst will change the process that the reactants go through to form the products. And that's only useful to add a catalyst if it's going to speed up the reaction. It does that by lowering the activation energy. So this catalyzed example here has now 2 reaction steps, but it's still faster than uncatalyzed because we have lower activation energies for both steps. So the rate determining step now requires this much activation energy relative to that much activation energy. So catalysts speed up the rate of reactions by lowering the activation energy. They provide an alternative pathway to go from reactants to products. That alternative pathway has lower activation energy. If you're adding something that changes the pathway but it increases the activation energy, there's no point in adding that. The goal is for the reaction to happen quicker. So adding the catalyst increases rate of reaction by lowering the activation energy through an alternative pathway. So they will have, this reaction will have different elementary steps than if the catalyst was not involved. But again, those steps will happen quicker than without the catalyst. Catalysts are always regenerated in a reaction. So for the catalyzed reaction coordinate diagram here, we have the reactants, which includes the catalyst. The catalyst and the reactants react together. They go through these two steps, and then we produce the products of the reactants of the reaction, and the catalyst is regenerated. So the catalyst, after the reaction is over, can be collected or reused. So it can be used for additional reactions. It is not completely used up. It is used in the reaction steps and then regenerated so it can be reused. Okay, so I've got an example with real molecules on the next slide. The decomposition of hydrogen peroxide, H2O2, has a very high activation energy. But if you add a catalyst, hydrogen bromide, for this reaction, the reaction occurs much faster, and it occurs through these two steps. So these are two elementary steps. We will write the overall reaction equation. Based on these elementary steps, and we'll identify, we're already told HBr is the catalyst, but we'll see what that looks like in these two steps, and then we'll identify an intermediate as well and see how that is different than a catalyst. So writing the overall equation, we have hydrogen peroxide, H2O2, present with 2 moles on the reactant side and nothing on the product. So we have 2 H2O2. Then we have 2 HBr on the reactant side and 2 HBr on the product side. So these get canceled out, but this is not an intermediate. This is different. It cancels out like an intermediate, but as a catalyst, remember the definition of a catalyst is that it gets regenerated. So it's first used up as a reactant to help the reaction move forward, and then it's regenerated by the end of the reaction. So this is a catalyst. HBr is the catalyst. The next reagent is Br2. Br2 is present on the left side and is present on the right side, so it also gets canceled out. But Br2 was first generated and then it was used up. So the catalyst was used up and then generated. Br2 was generated and then used up. Br2 is an intermediate. So that's what we are more familiar with. Br2 as an intermediate is first produced by the first reaction and then is used up in another reaction. That's different from HBr, which was first added as a reagent and used up, and then it was produced. So I'm just writing here that HBr, the catalyst, was consumed and then reproduced. All right, and that's all for reagents. So we're done with the reagent side. Going to the product side, we have 2 moles of H2O and 1 mole of O2. And that takes care of everything. So notice that when the catalyst is used, the overall reaction equation is the same as without the catalyst. It's still the same reactants and products, but we're adding that catalyst that gets regenerated to make the reaction go quicker. Questions on this? Y'all feel confident in identifying a catalyst and a intermediate, deciphering between them? Can I offer an explanation, a re-explanation of anything? Yeah, thank you, yes.
I just have a question. So when it comes to the two things, or things like being canceled out, like
Yeah.
out of the overall equation, so that is only going to be like an intermediate or a catalyst?
Yes.
Like either or, just those two will be canceled out.
Yes. For the elementary steps that we are working with, we will be canceling out intermediates or catalysts. Sometimes, we saw an example on Monday where we had 2 moles of something over here and 1 mole over here. So they're not completely canceled out because they were in a 2-to-1 ratio. So we still had, in the end, 1 mole on the left side.
Oh, okay.
It was a reagent that also became a intermediate.
Thank you.
Yeah. All right, I'll be satisfied with one question. You all heard of a catalytic converter in a car? No, maybe. Maybe some of you have. Okay, well, a catalytic converter exists in a car. Your car will have one. The catalytic converter is a part of the car that takes the exhaust of your engine, which produces harmful toxic gases, and converts it with a catalyst to less harmful gases. So the catalytic converter has a heterogeneous catalyst. We'll talk about what that means in a second. But that's a solid surface here. The exhaust from your car goes through and interacts with this solid catalyst. And then safer gases, carbon dioxide, N2O, and H2O, are then produced through that chemical reaction that's catalyzed by the surface of the catalytic converter. A heterogeneous catalyst is a catalyst that is in a different phase from the reactants. So here we have a solid catalyst reacting with gaseous molecules, 2 different phases. Phases, we're thinking solid, liquid, gas. So we call that a heterogeneous catalyst. We're going to write that down just to make sure it's written in your notes. So if the catalyst is in a different phase, heterogeneous catalyst. If it is in the same phase as reactants, we have a homogeneous catalyst. If you look back at the previous slide, the reagent, hydrogen peroxide, was in aqueous solution. The catalyst, hydrogen bromide, was an aqueous solution. So those two, the reactant and the catalyst, are in the same phase. So that was a homogeneous catalyst. Here we have solid catalyst, gaseous reactants, so heterogeneous catalyst. All right, I've got 2 more questions to wrap up chapter 14 about catalysts. So I'll give you all a few minutes to work on these, and then we will review and possibly start 15. So first one, you've got 2 elementary steps and you're identifying intermediate and or catalyst. Second one, just find the correct statement about a catalyst.
Okay, so can you identify, like, if there is an intermediate?
When you say design, you say the, is it B or two intermediate?
So there's, yeah, so in those 2 reactions, there's BR2 and there's HBr. The BR2 is an intermediate because it's produced in the first reaction and then well, it's not an intermediate. It is sometimes, but it's not an intermediate. Yeah, because it's used up first and then it's reproduced, so that's a catalyst. An intermediate is produced and then it's used.
Would be easy.
Which one?
The first one. No, B C.
A minute or 2.
All right, I'll end it here. All right, we've got these 2 elementary steps. We're looking for any intermediate and any catalyst. So really, we're looking for something that is on both sides of the reaction equation, the left side of one, the right side of another. And then we have to determine which one is first consumed and then produced, and which one is first produced and then consumed. So we notice, for example, C is used as a reagent and it's produced in the second step. So what is that? Catalyst, what we just learned about. Used to speed up the reaction, but it's always regenerated. So that's a catalyst. And then, let's see, A2, B2 is only on the left side. BC is on the left and the right. It is produced in the first reaction and then used up in the second. So what is that one? An intermediate. Produced and then consumed is an intermediate. Consumed and then produced is a catalyst. So A is our correct answer here. Then next, we're identifying the true statement about catalysts. First says heterogeneous catalysts are always solid. That is not true. We could have a gaseous phase reaction and a liquid phase catalyst. That would be a heterogeneous catalyst, vice versa. B, homogeneous catalysts are always liquids. Also not true. We could have a gas phase reaction with a gas phase catalyst or solid phase reaction with a solid phase catalyst. C says catalysts speed up chemical reactions by increasing the activation energy. Well, increasing the activation energy of a reaction would mean that the reaction occurs slower. It's increasing the energy required for the reaction to occur. So that's definitely not speeding up any reaction. D, catalysts increase the temperature of chemical reactions. We've not talked about temperature this section. Increasing temperature would increase the rate, Adding a catalyst would increase the rate, but those are two different things. A catalyst is the material, temperature is adding energy. And then E, catalysts do not appear in the overall reaction equation. That's true. They always get canceled out because they're used up and then they are generated. So we've got E. Okay, questions on these two questions? We are going to briefly begin 15. We are going to continue talking about chemical reactions here. We're talking about a specific type of reaction in chapter 15, which are, do you guys have a question? You're talking quite loud for lecture time. Thank you. We are talking about specific types of reactions that happen in the forward reaction. We've got reactants forming products, but also those products can then reverse and form reactants. So we're going in both directions, and they will reach an equilibrium. So here are the different sections, and we are just starting with an introduction to equilibrium. So I've got an example here. This first scenario, another chemical reaction, we have H2 gas forming and reacting with N2 gas. With a catalyst and heat present, this will form NH3. So we've got two reagents forming a product. Oftentimes, if heat or a catalyst is required for a reaction, it will be included above or below the reaction arrow. Sometimes it's included on the left side, but sometimes above or below the arrow. So if you have H2 and N2, they'll form NH3. If you have NH3 with a catalyst and heat present, it will decompose and form H2 and N2. So for this reaction, for many reactions, with H2 and N2 present, that will form NH3. But when NH3 is also present, it will form H2 and N2. So we've got these reactants forming the product in the top reaction, and then the product of the top reaction forming reactants from that, which are included as products here. So it doesn't matter if you have a chamber and you add NH3 gas, then some of that NH3 will produce H2 and N2. And then also the H2 and N2 will then produce NH3. Or if you start with a chamber with H2 and N2, they will react to form NH3. As NH3 is produced, it will break down into H2 and N2. So those two reactions are both occurring, and they occur at they're both constantly occurring, and they will reach an equilibrium where we have a constant concentration of each reactant and product. Kind of like we talked about vapor pressure dynamic equilibrium, where you have a liquid evaporating, liquid particles are escaping into the gaseous phase. At the same time, gaseous particles are condensing into a liquid phase. We're not changing the concentration of gas or liquid, but they're both changing phases. When we have an equilibrium reaction, the concentration of reactants and products doesn't change, but reactants are always forming products and products are always forming reactants. So we can write an equilibrium equation for this reaction by having, I'll just use red, 3H2 gas. We write the balanced equation. But between reactants and products, we have this special equilibrium arrow that has half of an arrowhead pointing to the products, half of an arrowhead pointing to the reactants. And this indicates that for this reaction equation, this reaction is in equilibrium. The products are in equilibrium with the reactants. Reactants form products, products form reactants. We've got a reversible reaction that reaches an equilibrium, and we can describe what that equilibrium state is. But you might imagine calculating concentrations of these And the rate of these reactions will add a layer of complexity, which we'll get to next week. Have a good weekend, everybody.